We'll focus on two primary algorithms used to locate an item in a list of information: linear search and the binary search. Linear search works by sequentially going through each element in the list until a match is found or the whole list has been searched. On the other side, binary search takes a more efficient approach by dividing the sorted list into halves and then narrowing down the search range until the item is located or determined to be absent. Linear search is also commonly referred to as a sequential search. The algorithm starts at the first element of the array and examines each item one by one in sequence until it either finds the target value or exhausts the entire list. It is a straightforward approach, but may not be the most efficient for large or sorted datasets, as we will contrast with binary search later on. Let's illustrate the linear search algorithm with an example. Consider an array num list containing the numbers 17, 23, 5, 11, 2, 29, and 3. If we are searching for the value 11, the algorithm will examine the elements 17, 23, 5, and finally 11. At this point, it finds the target value and stops. However, if we are searching for a value not present in the list, let's say 7, the algorithm will examine every element 17, 23, 5, 11, 2, 29, and 3. Since it doesn't find 7, it will go through the entire array. This example showcases both the simplicity and the potential inefficiency of linear search, especially when dealing with larger or sorted lists. Now let's walk through the algorithm for linear search step by step. Initialize 3 variables. Found is set to false. Position is set to -1. And the index start at 0. A while loop starts running as long as index is less than the number of elements in the list and the found is still false. Inside the loop, we check if the current element indicated by list subscript index is equal to the search value. If it is, found is set to true and the position is updated to the current index. After the if statement, or if the condition is not met, index is incremented by 1. The loop continues until either found becomes true or the index reaches the end of the list. Finally, the position variable is returned, which will be -1 if the item was not found. So this algorithm gives you not just a yes or no answer, but also the position where the search value is located if it is present in the list. In this slide, we present the C++ implementation of the linear search algorithm. The function linear search takes an integer array, ARR, its size, S-I-Z-E, and the value we are looking for, which is value, as arguments. We start by initializing index to 0 for array traversal, position to -1 for recording where we find our value, and the Boolean found to false. A while loop starts, which will continue as long as index is less than size and the found is false. Inside the loop, we check if the current array element ARR subscript index is equal to our search value. If it is, we set found to true and position to the current index. Regardless of the if condition, index is incremented by 1 to move to the next element in the array. Finally, the function returns position, which will be -1 if the value was not found in the array. If it is found is the recorded value's subscript. We are doing this inside the if statement in the while loop. The pros of a linear search are easy to understand. The algorithm is quite straightforward in making it accessible even for those new to computer science. Unsorted data, one of the key advantages is that it can work on array in any order, whether sorted or unsorted. The disadvantage are it's inefficient. It's not the most time-efficient algorithm, especially for large data sets. On average, it examines n divided by 2 elements when the value is in the array. If the value is not present, it goes through all n elements, which can be quite slow for large arrays. Now let's talk about binary search, another algorithm for locating an item in a list. Unlike linear search, this method requires the array to be sorted in ascending or descending order. So binary search divides the array into 3 sections: the middle element, the elements to the left of it, and the elements to the right. The algorithm then compares the middle element with the target value. If it's a match, the search is done. If not, the algorithm repeats from step 1, but only on the half of the array where the value could logically be found. This process continues, narrowing down the potential location in a divide and conquer manner until the value is found or there are no more elements to examine. By repeatedly halving the section of the array where the target could be, binary search achieves significantly better efficiency compared to linear search, especially to large sorted datasets. Let's apply binary search to an example for better understanding. Assume we have a sorted array, numList2, containing the elements 2, 3, 5, 11, 17, 23, and 29. If we are searching for the value 11, the algorithm first looks at the middle element, which is 11. In this case, it finds the target value immediately and stops. As you can see, just one comparison is needed, showcasing the efficiency of binary search. Now, if we are searching for the value 7, the algorithm initially examines 11, the middle element. Since 7 is smaller than 11, it narrows the search to the first half of the array, 2, 3, 5. The new middle element is 3, still no match, but 7 is greater than 3, so it looks the upper half of the remaining elements, which is just a number 5. Still no match. And with no more elements left to examine in the potential range, the algorithm stops. So in the second case, only 3 elements are examined to conclude that 7 is not in the array. This demonstrates again the efficiency of binary search compared to linear search, which would have examined all 7 elements. In this slide, we outline the general algorithm steps of binary search. So first, we initialize first to 0 and the last to the last index of the array. Also, set a found flag to false and the position to -1. Enter a while loop that runs as long as found is false and the first is less than or equal to last. Inside the loop, calculate middle as the index halfway between first and the last. Compare the middle element, array subscript middle, to the desired value. If it's a match, set found to true and the position to middle. If the middle element is greater than the desired value, set last to middle -1 to narrow down to the lower half. Otherwise, set first to middle +1 to examine the upper half. Continue this process in the loop until either found becomes true or the first exceeds last. Finally, return the position, which will be -1 if the element is not found. The function binary search takes an integer array, its size, and the target value to be located. We start by initializing variables. First is set to 0, last is set to size -1, and the position to -1. We also have a Boolean flag found set to false. A while loop starts and continues as long as found is false and the first is less than or equal to last. Inside the loop, we calculate the midpoint index, middle, as the average of first and the last. We then compare the middle element, array subscript middle, to the target value. If it is a match, found is set to true and the position is updated to middle. If array subscript middle is greater than value, we adjust last to middle -1, essentially ignoring the upper half of the current segment. Otherwise, we set first to middle +1, focusing on the upper half of the array. The function ultimately returns position, which will indicate where the value is located in the array, or -1 if not found. For binary search algorithm, the most significant advantage is its efficiency. For an array with n elements, it performs at most log to n comparisons, making it much faster than linear search, especially for large data sets. Disadvantage is it requires the array to be sorted. If the array is not sorted, you will either have to sort it first, which has its own computational cost, or resort to using a different algorithm like linear search. To sum it up, binary search offers a higher efficiency method for finding elements in sorted arrays, but this comes with the precondition that the array must be sorted in advance. Sorting can be applied in various ways. Alphabetical for arranging text-based data, ascending numerical for arranging numbers from smallest to largest, and descending numerical for arranging numbers from largest to smallest. We will be exploring two fundamental sorting algorithms: bubble sort, a simple but often less efficient algorithm that repeatedly swaps adjacent elements if they are in the wrong order. Selection sort, another straightforward algorithm that selects the smallest or largest element from the unsorted portion and swap it with the first unsorted element. Both algorithms have their own set of benefits and drawbacks, which we will dive into the following slide. Bubble sort starts by comparing the first two elements in the array. If they are out of order, swap them to correct their positions. Move down the array by one element and now compare the second and the third elements. Again, swap them if they are out of order. Continue this process of comparing and swapping adjacent elements until you reach the end of the array. Once you complete one pass through the array, start again from the beginning. Keep making these passes until you can go through the entire array without making a single swap. When you complete a pass with no swaps, the array is sorted and the algorithm terminates. We have an array numList3 containing the elements 17, 23, 5, and 11. First, we compare the elements 17 and 23. They are in correct order ascending, so no exchange is needed. Next, we compare 23 and 5. These are not in the correct order, so we swap them and the array becomes 17, 5, 23, and 11. Finally, we compare 23 and 11. Again, these are out of order, so we swap them. The array now reads 17, 5, 11, 23. Note that after one pass, the largest number 23 has bubbled up to its correct position at the end of the array. Now let's proceed with the second pass. The first comparison is between 17 and 5. These numbers are out of order, so we swap them. The array becomes 5, 17, 11, 23. Next, we compare 17 and 11. Again, these are out of order, so we swap them. The array now reads 5, 11, 17, 23. Finally, we compare 17 and 23. These numbers are in the correct order, so no exchange is necessary. With the second pass, the array becomes 5, 11, 17, 23, which is now sorted. Notice how each pass bubbles up the next largest element to its proper position, thus the name bubble sort. After second pass, the array contains 5, 11, 17, 23. First, we compare the values 5 and 7. They are in the correct order, so no exchange is needed. Next, we'll compare 11 and 17. These are also in correct order again. No exchange is necessary. Finally, we compare 17 and 23. They too are in the correct order, so no swap is needed. After this second pass, we observe that we made no changes. This is a clear indicator that the array is fully sorted. Therefore, we can conclude that the sorting process is complete, and the array is now in ascending order 5, 11, 17, and 23. This example shows how bubble sort iteratively works its way through the array, making the necessary swaps until no more are needed, confirming that the array is sorted. Here's the code implementing the bubble sort algorithm and the auxiliary swap function. The bubble sort function accepts an integer array and its size as arguments. We have two nested loops. The outer loop runs from size -1 down to 1 and controls the number of passes. The inner loop iterates through the array from the beginning to the max element, performing the comparison and the swaps. Inside the inner loop, we use an if statement to compare adjacent elements. If an element is greater than its adjacent element, we swap them using the swap function. The swap function is straightforward. It uses a temporary variable, temp, to facilitate the swapping of two variables in memory. The function swap is a built-in function in the C++ standard template library which swap the value of two variables. So you don't really need to implement this swap function in your code. You can just make a function call swap. It will be fine. Line 57 to 62 can be omitted. Bubble sort is easy to understand in the implement, making it a popular choice for simple sorting tasks and educational purpose. The algorithm is slow for large arrays and generally considered inefficient compared to other sorting algorithms, especially when performance is a key requirement. In this slide, we introduce another sorting algorithm, selection sort. Start by locating the smallest element in the array. Once you find it, sort it with the array at the first position, for example, index 0. Next, identify the smallest element from the remaining portion of the array and swap it with the element at the second position, which is index 1. Continue this process of finding the smallest element in the unsorted section and swapping with the first unsorted element until you have moved through the entire array. When you are done, your array will be sorted in ascending order. Let's go through an example. We have an array num list containing the elements 11, 2, 29, and 3. The first step is to identify the smallest element in the array. In this case, that's the number 2. Next, we swap the smallest element with the element at the first position, which is index 0 in the array. This results the array becoming 2, 11, 29, and 3. Notice how the smallest number 2 is now in its final sorted position at the beginning of the array. The next smallest element in the unsorted portion, so we ignore the first element which is already sorted. So the next smallest element in the unsorted portion is 3. We swap it with the element at the second position, which is index 1. Now the array becomes 2, 3, 29, 11. Moving on, we find the next smallest element in the remaining sorted section, which is 11. We swap this with the element at the third position, which is index 2. The array then reads 2, 3, 11, 29. At this point, the array is fully sorted, 2, 3, 11, 29. Notice how each pass places the next smallest element in its final sorted position. This means that the array gets sorted with relatively fewer swaps. The selection sort function takes an integer array and its size as arguments. It initiates with a for loop that iterates from the start of the array to the second to last element. Within each iteration, min index is set to the starting index, and the min value is set to the value of the element at the starting index. Another for loop starts, this one running from start plus 1 to the end of the array. Inside this loop, each element is checked to see if it is smaller than min value. If it is, min value and the min index are updated. After identifying the smallest element in the unsorted part, we swap it with the element at the start index using our swap function. This process repeats until the array is fully sorted. One of the key advantages of selection sort over bubble sort is that it generally makes fewer exchanges. This can be particularly beneficial in cases where the cost of swapping elements is high. While selection sort is relatively simple, it might not be as intuitively easy to understand as bubble sort, especially for those who are new to programming or algorithms. In many cases, you'll find yourself working with vectors instead of arrays. Many sorting and searching algorithms can be adapted to work with vectors, with only minor modifications. When defining a function that takes a vector as an argument, you can use vector, angle bracket, you specify the type, and ampersand in the function prototype to pass it by reference. This allows you to modify the original vector. Unlike arrays, vectors in C++ are dynamic, meaning they can grow or shrink at runtime. This eliminates the need to pass the size of the vector as a separate argument. You can use vector's size member function to get the current size of the vector. This program shows how to sort and search a vector of strings using two algorithms, selection sort for sorting and binary search for searching. We utilize the vector class to make the code more dynamic. We use a vector string named names to store a list of names. This allows us to dynamically add, remove, or modify names without worrying about its size. The selection sort function sorts the vector in ascending alphabetical order. We have adapted the selection sort algorithm to work with vectors of strings, ensuring names appear in a sorted manner. We use binary search to find a specific name within the sorted vector. Binary search is a fast searching algorithm, but it requires that the vector be sorted first, which is why we sort it with selection sort. The user is prompted to enter a name to search for. The program then uses the binary search function to find the name in the sorted vector and displays the position at which it's found, if at all. The function selection sort takes a reference to vector string. This enables it to modify the original vector passed to it. We identify the smallest string element in a subarray and swap it to the correct location. This repeats until the entire array is sorted. The algorithm is adapted to work with string objects, and the swapping operation is handled by the standard swap function. Binary search performs a search on a sorted vector string to find the given string. We keep adjusting our search range by having the array segment we are looking at, making the search operation efficient. If the string is found, the function returns its index position in the vector. Otherwise, it returns -1 to indicate that the string is not found in the vector. Both algorithms automatically adapt to the vector size by using vector size member function. From this example, we see the sorting and the searching algorithm, selection sort and binary search can also be used for the vectors.